So, well, one of the most important things we want to analyze of a graph is not whether it's symmetry, whether it's a symmetry, it has a symmetry about the x-axis, the y-axis, or no symmetry at all, because many natural phenomena are, of course, modeled by functions, and well, in some cases, like in maybe in biology, for instance, or in finance. For instance, in biology, in a chemistry class, for instance, when you are monitoring the profile of a chemical reaction, for instance, well, what you do is measure the concentration of, say, of one of the reactants and see at what rate it decreases, or maybe the concentration of a product, how in that case increases. Well, those words increasing, decreasing, well, we in those applications in science or in bacteria growth, well, these are described by, in a way, by mathematical functions. And well, as we have seen in some of the graphs of the functions, we have seen how graphs tend to decrease or increase, and in some cases remain constant. And well, this is one example right here of how we're going to do it. So in this case, well, uh, they're asking us to use the graph of the function below to determine the intervals where the function is increasing, decreasing, or remains constant. Well, so, and again, we need to be careful when stating the intervals here and when interpreting the graph, because recall that we always scan the graph from left to right, as if we were finding the domain. I mean, never from right to left, because we go with the order of the numbers from smaller to large. All right, okay, so let's go about it. My advice here, well, I'm gonna highlight with red the intervals, the parts of the graph that we see decreasing, and well, that's actually this portion of the graph. That's where the graph decreases. Well, that I'm going to use red for decreasing. I'm going to use green for increasing. So that's going to be all this interval right here. And then notice how between between x equals to 0 and x equals to 3, the graph remains constant. I'm going to use yellow for this. Remains constant because it neither increases nor decreases. And then the graph goes down again, goes down the hill. That is, decreases. All right. Another way to describe this, you can use signs if you want. What's that? Let me use red. Let me use red for to denote a decay, a decrease. It's going down, and then let me use green. Let me use the plus symbol to denote that the graph is going up, is increasing. And well, for the part that remains flat, I'm just going to use like a zero number. Well, actually, I'm going with, like, for those of you who have taken a chemistry class, the negative is used for electron, positive for protons, and the neutrons, where there's no charge at all, you use the zero symbol. All right, in a way, it's a zero symbol because there's no, it's null, if you will, no increase, no decrease. And then let's go again with going down, negative, 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 negative. All right. All right, let's see. So in this case, let's list the intervals at which the function increases. So it's increasing. It's increasing over the interval. Well, all we're going to do is, in this case, list the green interval. It goes between x equals to -4 all the way to x equals to 0. We don't do the y value. We just do the x value. And in this case, careful, we're going to use parentheses, because if we do the inclusive, well, exactly at the point, it's neither increasing nor decreasing. In fact, at this point right here, well, it's flat. So that's why we don't consider the exact same point. So just we leave it only as an open interval. And well, that's the only interval where the function is increasing. So now how about let's list the interval where the function is decreasing. And well, in this case, notice there's two intervals that are marked with red. The one that goes between -6 and -4, and the interval that goes between 3 all the way to x equals to 6. So we need to list these two intervals, well, -6 all the way to -4, and then put a union symbol, like as if we were writing a domain, and then express the other region in red that shows the decreasing, with also with interval notation, and that goes between 3 and 6. All right, and lastly, constant. That is the interval where the function neither increases nor decreases, which is precisely this part in yellow where it remains flat. That goes from x equals to 0 to x equals to 3. And again, exclusive, 0 to 3. All right. And to wrap up this section, well, we are going to further describe more properties of functions from a graph. Well, so the fact that we see this behavior of functions increasing, decreasing, constant or flat, depending on the word you prefer to use, either way is fine. Well, we want to locate maximum and minimum values, but there's a couple of there's two different maximums and two different minimums. There is what we call relative maximum and relative minimum, and there is what we call absolute maximum and absolute minimum. Well, number one, how to identify these maximum and minimum values? Well, by observing the behavior of the graph. Notice how well if we think again of that of the hiking example we talked about last time. So noticing how when we go hiking, we go down the hill, we go up the hill, we go all over the place, right? So the behavior here is when we go down the hill and then we go up the hill, that means we reach a minimum value somewhere in between, right? And then if we keep going up, we keep increasing, and then we go decreasing. That means there is a maximum value related again. Now, well, notice, okay, so from the picture here, we can easily identify the maximum and the minimum values here because, well, I mean, minimum means the smallest, maximum means the largest. Well, but here's the problem. Here, if we talk about the maximum, okay, this one is maximum, and this one is another maximum. However, one of the maximums is larger than the other maximum. Which of these two maximum values is larger? 210. The 210 it's more maximum than the other. So actually, the largest of the maximum values, it's what we call the absolute. I mean, the absolute, the largest, and everything else that looks like a maximum still, it's just called relative maximum. And likewise, for minimum values, let me circle them with a different color. That's a minimum, that's another minimum, and there's this other third minimum. Well, yes, that looks like a minimum value. That's because we go decreasing and then increasing, decreasing, then increasing, and again decreasing and then increasing. However, only one of all those maximums, or well, potentially more than one, not necessarily just one, is going to be the absolute minimum, and that's going to be the smallest of the minimums themselves. And in this case, this is the absolute minimum because this is the lowest of them. Yes, these two are still minimum values. However, those are just relative minimum values. Let's answer the questions here. Okay, what are the numbers? First of all, be careful with the wording of the question. What are the numbers, if any, at which f has what's that? A maximum. Okay. Here first, they're asking us for what values of x do we have local maximums. Again, what's the value of x at which we have a local maximum? Just the value of x. Negative 2. So x equals, at x equals to negative 2. And they're asking us now for the local maximum, that is the y value. So the local maximum value, that'll be y equals to the corresponding y value of the order pair. All right. And looks like there's only one local maximum. There's no other local maximum. The other maximum will be the absolute maximum. Now let's look at part B. What are the numbers, if any, at which f has a minimum but a local minimum in this case? And then same. So what are those local minimum values? So number one, let's list the values of x, if any, at which we have local minimum. What are they? Yes. 0 and 0 and 5. All right, and then the local minimum is going to be whatever y value is related to each of the, well, in this case, since it's the same y value, well, so that'll be y equals to 0 and for both. Right? So y equals 0 for both. Okay, so we're done with the local values. So now let's look at the absolute values here. So what are the numbers, if any, at which f has an absolute maximum? All right. So what value of x? 2. So that's at x equals to 2. And the absolute max, not a local, the absolute maximum will be y equals to 10 in this case, right? And lastly, okay, same for the absolute, but in this case for the absolute minimum. So we already listed the two relative minimum. Now we need to list the absolute minimum. What value of x is going to give us the absolute minimum? Negative 8. At x equals to negative 8, and the absolute minimum at the absolute minimum, which is y equals to negative 4. All right. So again, it's just to identify these order pairs from the graph. Of course, when you get to calculus, you are going to solve this problem in a different way. Though some of you might have already taken calculus in high school, you know what to do. You will be given a function. You will have to find the derivative of the function, set it equal to 0 to find the critical values, and then construct a behavior table to show the intervals where the function increases, decreases. Based on that, you will make conclusions about whether you will have maximums and minimums. But I mean, that's for those of you who have already taken calculus. Those of you who haven't, well, you'll see that in Math 150, maybe 2 semesters from now or so. All right, so let's see. This is a wrap up for section 2.3. Okay.